We're going to start off by taking a more in-depth look at this Sql Select statement. This is something that you're undoubtedly familiar with from previous experience, but we're going to try to unpack all of the functions and details and different clauses that can be used with a Sql Select. Let me start out by encouraging you to read the manual. I know that there's a lot of pushback sometimes from students who are not that keen on trying to read a lot of material, but I have to tell you the unfortunate news is that if you really want to become an expert at something, it's almost impossible to do that without actually stopping to read the details. And for SQL, the best place to go to learn about the select statement is to the documentation. There's an unfortunate term of art here, RTFM, which stands for Read the Fine Manual, except that fine is usually replaced by another word that starts with F. Sorry for the shocking opening to this talk, but that's actually the term of art. So if you hear somebody say RTFM, that's what they're talking about. I've put some stuff here on this slide that you can take advantage of to link to the SQL documentation for Postgres, which is the database we'll be using for this relational database section of the course. So just in general, a good place to know how to find. In particular, when you're looking at documentation, and this is true of any kind of technical documentation, not just with respect to Postgres, it's really helpful to understand the organization of the document. So I've put in a link here to the overview page for the documentation that gives you a sense of the structure. And often there'll be like tutorial information, and then perhaps reference manuals, and then some appendix or appendices that give you a little bit more detail than you might want to consider at first glance. It's also really important when you're thinking about using documentation to understand the conventions that are being used. So for example, in the Postgres documentation, this information in here shows you some of the things that they use as conventions for presenting information. So for example, in the descriptions of the select statement, they use square brackets to indicate something that's optional. So obviously we'll see here throughout the course of this talk that there's different clauses that you can add to the SQL Select statement that you can use optionally, and those would appear in the documentation with those brackets. In some cases, there's different options where you can choose one of the following, and in the Postgres documentation they use curly braces to indicate those sorts of choose one situations, and they separate the options with a vertical bar. Now these aren't universal conventions for every kind of documentation, but I would say that they're not unusual, and it's important to know what they mean. And then finally, because you can in some cases repeat parts of a command multiple times, the Postgres documentation uses the ellipsis or the three dots to indicate that you can repeat the preceding thing multiple times. So those are just some simple examples of documentation conventions that you should really be aware of as you're looking at the details of how to use the select statement. So again, I would encourage you to take a few minutes and go and actually click through this link from the slides and look through the SQL documentation for the select statement. You'll get familiar with how these conventions are used. You might find some things that you weren't aware of before. And just in general, you'll find the place where you can actually become a real expert at using this statement, and all of the mysteries and the details are revealed in the documentation. So always a good idea to RTFM. Okay, so we're going to take a look at the select statement, and I'm going to cover each of the various clauses that can go into that statement in the order that I've shown here. And we're going to use a specific kind of syntax called a railroad diagram, which I'll give you some information about here in a second. But the idea here is that these various keywords, and I guess they're key phrases grouped by and order by, can appear in various contexts inside the select statement, and part of learning how to use it effectively is seeing what those constructs look like. So let's just start out with the basic form of the select statement. And this top portion of the page here is an example of a railroad diagram. The idea here is that if you want to be able to express the syntax of some complex statement, like a select statement, you can have a graphical representation of how that statement is formed. So we always start out entering the railroad diagram with this right pointing arrow that comes from nowhere. and then follow through the diagram according to the various paths that lead through the railroad yard here. So the first thing we see that we have to include in a select statement is actually the select keyword. So these roundy boxes with the teletype style characters inside them have to be used as literals. And any path that you can take through this railroad diagram represents a syntactically correct way of formulating the statement. So for example, we might do something quite simple where we can, let's say we just want to select all the fields in a particular table. We would just say select star. Then we of course have to follow that up with a from clause, but that's in a different portion of this presentation. So in order to verify that select star is actually correct, we'd see that we could enter the railroad diagram, select, and then we could take this path through the diagram. We'd have to then put in a star, and then we can get all the way to the exit of the diagram here on the right hand side. So select star is a syntactically valid select statement. If and you can see here at the beginning of the railroad diagram, that little branching point, we could also say select distinct. If we want to only get unique rows in the output set, we can follow the railroad diagram by first using select and then going to the distinct and output, adding that to our select statement. And then from there, we might just say star and then exit the diagram. So just like select star is a valid select clause, so is select distinct star. More interestingly, let me back off some of these decorations so I'm not cluttering it as much as I was. More interestingly, we're often going to have in a select statement a list of the column names that we want to be able to fetch out from the query. So a more common path through here would be select, and then take this path through the railroad diagram to where we see an expression. Now here we've got a different type of graphical representation here. So while these roundy boxes with the typewriter characters in them represent keywords, the square boxes that have an italicized entry in them represent something more complex. In this particular case, it's called an expression. And in Sql, what we're going to typically see there would be the name of a column. But we'll see that we can actually do more complex things in those expressions than just a column name. Oftentimes, we're going to have multiple columns. So the railroad diagram allows us to express repetition. So if we say select and then take the skip over the distinct part, select and then say some column name, first name, for example, and then we can take this path through the railroad diagram and loop back around to get ready to output another column name, but we see that we go through a comma, so we have to put a comma between column names, and then we can end up back here and enter another expression. So we could say select first name, comma, last name, comma, address, and so forth until we run out of columns that we want to use. And then instead of looping back around for another one, we can exit through this path out of the railroad diagram. So you can see this is just kind of a nice graphical way of representing information about what's syntactically valid in the select statement. In this case, just the select clause itself. The other thing here in this diagram is this output name box. So we can include as part of the list of columns or list of expressions that we're trying to fish out of the underlying query, we can specify the name that's going to be used for that column. So if the expression is a little bit more complex and we want to have a simple column name in our output result set, we can give a string that's going to be used as the output name. So here's a simple example of a select query. Select country ID, comma, country from the country table. This is actually data from our little DVD rental sample database. And I've added, as a third line here, a limit clause. We'll talk about that a little bit more, but basically what this says is go get the whole result set and then just chop off the first n rows. So it just tells me, or tells the query engine to just give me 10 rows. And I'm only doing that so that the result set here fits on the slide. It'd be totally fine for most of these examples to just ignore those limit statements, because they're just there to keep the result set from spilling off the end of the page. So obviously we get in the result set the country ID and the country itself. So nothing particularly earth-shattering there. As I mentioned back here in the railroad diagram, we saw that with the as keyword we could give an alias to the name of the column. So that's what's going on here. I've got select country ID as ID and country as name. And you can see that the query engine gives us back the same data as previously, but now the column names are headed by the string that's associated with that as clause. And it's it's not super helpful here when we have a reasonable identifier coming out of the database schema, but it tends to be more helpful if we've got a more complex expression here in the select clause, and we want to have a simple way of referring to it in the result set. We also saw that we had in the railroad diagram this distinct keyword, and the idea there is that it's going to eliminate duplicate rows from the result set. Of course, in the schema for the database table, we're always going to have primary keys that are going to not ever have duplicates and that kind of thing. But if we're running a query that doesn't involve selecting things by primary key, or even sometimes if we do, we might end up with multiple copies of the same values showing up in the result set. So that distinct keyword is a help there. Now here, what I'm showing you is a query without the distinct keyword. So I'm just asking for the country ID from the city table. And in order to force this into a particular order here where we have multiple consecutive rows in the result set, I'm using the order by clause, which you're probably familiar with from previously, but I'm just ordering this output by that value. And you can see we have multiple instances of 2, multiple instances of 4, multiple instances of 6, because multiple of the cities have the same country ID. Now the next example then is going to add the same query, except we've brought in the distinct keyword. So given this first result set, we're basically going to sort of squish down the rows of that result set that have identical values. So with the distinct keyword, we see that we only have one instance of 2 instead of 3. We have one instance of 4 instead of 2, one instance of 6, and so forth. So that's the purpose of the distinct keyword. Okay, so far we've been assuming that we know all about the from clause here, but let's unpack that in a little bit more detail. So here's the railroad diagram giving us the syntax of the from clause. So we start out with the keyword from, and then we name a table. And then one path through the railroad diagram takes us directly to the end of the clause, and that would correspond to something like this previous example where we're just naming a single table from which we're going to extract columns according to the column list in the select clause of the statement. More interestingly, the from clause can be used to do table joins. So we recall that a join basically allows you to combine rows from multiple tables, usually, well, from 2 tables at a time, and then you can compound that as you go. So for example, if we have a table here that maybe has our cities, so this is the city table, and we have another table that would have our countries. We're going to have a bunch of rows of cities, a bunch of rows of countries, and a join of these 2 tables is, in its simplest possible form, would take and pair each city to every country. So the first one, then the second city to every country, and then the third city to every country. So if we had, for example, 100 cities and 10 countries, we would end up with each of those 100 cities paired with each of those 10 countries. We'd have an intermediate result set of 1,000 rows, right, with each city paired with each country. If we had in order to do that, we would say something like select star from city, inner join, country. I guess I have a little error here in my railroad diagram in that you can actually avoid that on condition if you wish. So select star from city, inner join, country, and that would be the end of the query, would give us back a result set that would contain every city paired with every country. In this case, it would be 1,000 rows. This is something called a Cartesian product. So that pairing of all possible rows from each of the two tables is called a Cartesian product. And it's sort of the default behavior that the join operation does for us in SQL. That said, that's not probably a super useful query, right? If we're going to come up with a query that looks at cities and countries, what we probably want to get is a list of all the cities together with the countries that those cities are located in. And in our schema, here in the city table, we're going to have some sort of a foreign key that has the ID of the country. And over here on the country side, we're going to have a primary key that is that country ID. Right? So if a particular city in here has country ID 7, then somewhere over here in the country table, we're going to have a primary key of 7. What we'd like to have in our result set is for that particular city, just have a single match to the country table that has the corresponding country information in it. And that's really what goes on when we add this on clause. I want to say something like join, from city, inner join country on city country ID equal to country ID, right? Where the value of the foreign key in the city table matches the value of the corresponding primary key in the country table. You can think of that on clause as a kind of a filter. If you think about this conceptually, when you're thinking about a join, the base operation is going to be to form that Cartesian product, right? Take all of the rows from the first table and pair them up with all of the rows in the second table in all possible combinations. But that's going to give us like way too much stuff in the output, right? And we're going to end up with those 1,000 rows, 900 of which are going to have a mismatched country and city. So what we do in that on clause is specify a condition that will be used to kind of filter out that Cartesian product, and the only rows that will survive that filtering process are the ones that satisfy this condition. So if the condition says only show me the rows where the foreign key from the city table matches a corresponding primary key from the country table, we'll only get those 100 rows paired with the appropriate country. I want to emphasize the notion that this is kind of the conceptual process, right? If we're thinking kind of through what is taking place here, it can be helpful for us to imagine, first of all, doing the Cartesian product, getting all the combinations, and then filtering those out according to the on condition. In implementations of databases, of course, they're not that inefficient. As they're working through these tables and using a variety of different optimization strategies in the implementations, they're not actually going to form that Cartesian product. They're going to end up going kind of directly to the result, including the on condition. But again, conceptually, it can be helpful for us to think about the query as taking place in that manner. Let's take a look at an example of doing these inner joins. So here's an example again from that DVD rental database example where we have a film table and we're joining it with a language table. So the film is information about a particular movie and the language is information about the language in which that film was filmed. And what we'd like to be able to do in a way that's very similar to the previous example we've been discussing with cities and countries is come up with a list of those films together, the film titles, together with the language in which they were filmed. So we're going to select the title and the language name as the two output columns from the film table, and we're going to do an inner join with the language table. Now if we just stopped right there, we would get our Cartesian product consisting of all the rows from the film table and all the rows of the language table in all possible combinations. Again, that's not particularly interesting. We really only want to have each film show up one time with its corresponding language. So the on clause sets the condition that will filter out rows from that Cartesian product. So we want to say that the language ID in the film table equals the language ID in the language table. So that equality comparison there is what determines which rows from that Cartesian product survive into the result set. Notice here also that, let me back out some of these underlines so we can see a little more clearly. The the use here of the name of the table and the name of a column in the table. And this is important in this case here because we can't just say language ID, because there's two instances of a column called language ID. So we need to provide some disambiguation here and say we want to compare the language ID column from the film table with the language ID column from the language table. Similarly, both of these tables have a name column, so the language.name here gives us the specific table that we want to reach into in order to expose the value of the name column. Here's an example of a many-to-many join. So in this case, we're doing a join between three different tables. So we're going to get the first name, the last name of the actor, and the title of the film that that actor is in. And we're going to start out by grabbing that information from the actor table. Now, so far we have access to the first name and the last name because those are both fields from the actor table, but we want to be able to join those to the films. Now, this is a many-to-many relationship. We've got the actor table, I'll just call it A here. Sorry. We've got the actor table A. We've got the film table F. And in order to get the many-to-many join, we have to have an associative table in between these two things. It's called film actor, FA. And there's a join, or there's a relationship between those things using the standard pattern for many-to-many relationships. So we can't just go directly from the actor table to the film table. We have to go through this intermediate film actor table in order to be able to extract the information we're interested in. So there's two joins going on. We're going to join actor to film actor, and we're going to join film actor to film. So the first from argument here is the name of the first table, the actor table, and then we're going to interjoin that with film actor. And we're going to supply an on clause in order to constrain those rows in that Cartesian product that we would conceptually get between actor and film actor, such that the actor ID in the actor table matches the actor ID foreign key from the film actor table. Now, as I've said before, in relational databases, everything is tables all the way down. Right? So if we were to just sort of stop right there, what we would be doing would be taking the actor table and the film actor table and joining them together according to this equality comparison, and the result would be another table, right? The result set is itself a table. But we want to do more than that, right? We want to sort of tack on some additional information to get the name of the film that that actor is in according to a particular row in the film actor table. So we're going to take that intermediate table that we've created from the first inner join, and we're going to interjoin that to another table. That's what's going on here in the second inner join clause, interjoin to film, and we don't want to get a Cartesian product between the first join and the film table. So we're going to add another on clause that's going to constrain that join to allow rows to survive only in the case that the film ID from the film actor associative table matches the film ID from the film table. That completes the query with the joins constrained appropriately to give us the information that we see in the result set here at the bottom of the page. I'm also doing a limit of 10, and just to illustrate another commonly used construct in Sql, there's an offset clause that says, in this case, basically skip to the 200th row of the result set that came out of this portion of the SQL query, and then the limit says give me 10 rows starting at that location. So these two things taken together are often used when you're trying to do like an interface that allows you to page through a larger data set. You'll go ask for the things at offset 0, and then if you're paging through things 20 at a time, you'll next ask for things at offset 20 with a limit of 20, then offset 40 with a limit of 20, and so forth. So those aren't really central to the discussion here, but just want you to understand what's going on there. So this gives us that many-to-many capability to join tables together. Now there's nothing that restricts you from doing joins of more than 3 tables. I can join 4, 5, 6, 10, 100 tables together conceptually. And in more complex databases and more complex applications, you might see joins that have quite a surprisingly large number of joins. The chief challenge with that is that this join operation is the most expensive operation pretty much that you can do when you're querying data from a database. So when we start talking about database normalization a little bit later, we'll start thinking about kind of the trade-off between normalizing data to get everything into its own separate table and the corresponding expense of joining those things back together in order to do a query from that database. Let's go back here and take a look at these other 2 join clauses. We've been specifying an inner join. And as I said, an inner join, when we use that on condition, is going to filter out the conceptually produced Cartesian product such that the value in some field on the first table matches the value in some field on the second table. Now, that's often what we want in situations where we have some reasonable guarantees that for every value of one field in the first table has some corresponding value in the second table, but that's not always the case. In particular, we might have columns in one or both of these tables that can take a null value. And you're familiar, probably at least informally from previous experience, that a null value basically just represents the idea that there is no information known about this particular field or this particular column in the table. So it's a completely legitimate thing to model in a database. But if we have columns that have those null values, say, for example, if we had allowed this foreign key in the city table to have a null value, then when we did this join between city and country, the corresponding city with that null value for the country ID would not match anything over here on the country table. That means it would basically fail to satisfy the condition from the on clause, and the resulting row would not show up in the result set. Now, in some cases, that's what we want, right? If we only want to get information about addresses that have a city corresponding to a country, then we're good to go. On the other hand, if we want to make sure that we see all of the data, whether or not there is a matching value in one or the other of the tables in the join, we're out of luck if we use the inner join. The left and right outer joins are what allow us to see data that has no corresponding value in the other side of the relationship. So when we use left outer join, what we'll see is that in the case where there is a value in the left-hand table but not a corresponding value in the right-hand table, we'll see that show up in the output with null values appearing in the fields that don't match. And for the right outer join, the converse is true. So we have sort of, if you think about the ordering of these tables in the clause, the first one you mention is the left table, and the second one is the right table, or before the left outer join and after the left outer join in the SQL statement. Let's take a look at the where clause. If you think about the select statement itself, when you write a select statement, the arguments directly to select are the names of the columns from the result set that you want to show up in the output. So in a way, the select itself allows you to kind of filter by column. The where clause allows you to do a similar thing, except now you're filtering by row. So after the Cartesian product is done, if there's a join, after the on criteria are applied to that Cartesian product, you're going to have a certain list of rows in an intermediate result set. And if you say nothing else, you're going to get all of those rows. But if you want to filter that further by row, that's where you add the where clause. So the where syntax actually is pretty complex, and I didn't take the time to try to draw a complete railroad diagram for it. But basically we're saying we want to do where followed by some condition. And that condition is always going to be a Boolean expression. So it's going to involve constants, literals, names of columns, different kinds of comparators, and so forth. But the idea here behind this being a Boolean expression is that for each of the rows in that intermediate result set, the database is going to apply that condition. And if that condition is true, the row will survive to the output. It's not any more complicated than that. So what can be in that condition? Well, we can have a column name if we want to compare a column name to a specific value or to a different column. Or if we need to, because of ambiguity in column names, we can say table name dot column name like we saw previously. We can do comparisons, so less than, greater than, less than or equal to, greater than or equal to, equality comparison. The not equal comparator is a little bit weird. It's sometimes called the spaceship operator. And there's also a comparator called like, which allows you to do some really simple string matching. And we'll look at some examples of that. So these comparisons are all binary comparators, right? You're comparing, say, a column to a constant or a column to another column. But you can build up more complex expressions by using Boolean operators. So I can connect those things together in the ways that you would expect. I can also use arithmetic expressions within these comparison conditions. So if I want to do add, subtract, multiply, divide, or modulus between fields to come up with different criterion for selecting rows, that's available to me. So here's a simple where clause. I'm going to grab the payment ID and the amount from the payment table where the amount is strictly less than $5. And you can see here's the first 10 rows of that result set. Quite straightforward, and of course the amounts conform to that where clause. Here's a little bit more elaborate one. First of all, this is the from clause has quite a lot more going on here. We're joining together the film table with the inventory table. So the film is just a list of all the possible films that a DVD rental place might have, and the inventory has to do with which of those films they have on hand right now. And they're going to join that together with a third table that represents a film that's been rented. And then when that rental takes place, there is a particular payment that the customer supplies to be able to rent the film. So we've got here actually a four-way join between film, inventory, rental, and payment. There's no real difference here from the previous many-to-many join that we looked at previously, right? We've got a join between two tables going on here. That results in a table because it's tables all the way down. That's going to then be joined with the rental table. And so there's going to be a table that comes out of that process. And that table is going to be joined with the payment table. And that's going to result in another table, right? So at the end of the day, this from clause is saying, here's how we want to formulate that intermediate result set. And if we just stopped there and we didn't add any on clauses, we'd have a Cartesian product of 4 different tables. So all possible combinations of rows from each of those 4 tables, which would be a totally legitimate query to issue to a database. Not probably something that's going to be super useful, though, in practice. We've also selected particular columns that are going to come out of this query. So just the title and the amount will show up in the final result set, even though we're joining together a bunch of other tables behind the scenes. And then finally, the where clause is going to give us specific rows in that result set such that all of these criteria are satisfied by those rows. So we want to get the amount being less than $5. We also want the amount to be greater than $1, so it's going to give us all of the values strictly between $1 and $5. And the payment has an associated staff ID, so this is basically the identifier of the person who did the rental. We just plugged in a constant value here of 2. And that's the end of the query. The limit here is just for presentation purposes. So the result here is something that looks like this, or the first 10 rows here. So we've got the title of the film and the amount that was paid to rent it. And in order to get from the title to the amount, we had to navigate from the film table to the inventory table to the rental table to the payment table. Notice also that this is just giving us information for the person who happens to have this staff ID, whatever that is. And it's also important here, as I've noted in this comment, that particular portion of the result set is available to us in the where clause, even though that staff ID doesn't get displayed in the resulting output, right? The output only shows the title and the amount, because that's what we asked for here in the select clause. But we still have access to all of the other columns in the result set that we've constructed here that we can use as part of the where clause. Again, even though that column doesn't show up in the output. Notice that this is the standard syntax for a comment in Sql. Because of the way this is being formatted, it shows up a little goofy. There's actually 2 hyphens that are there in the source code. So if you want to put a comment in line inside of a query, the common syntax is to have 2 dashes, 2 hyphens. Most of these things you're probably already familiar with from past experience with Sql. The group by might be something that is a little less clear-cut to you, or something you have a little less experience with. Group by is basically a way to aggregate data, is the most common use for it. So if I want to have sort of a summary, for example, of the amount of sales that are made in each of the states of the U.S. where my company operates, I can use group by to condense down sales data to just show me the list of states and then say the total revenue in each of those states. The syntax is shown by the railroad diagram here is straightforward. We say group by, and then we have this rather generically named grouping element, and we can have multiple of those grouping elements by separating them with commas, and that takes us out of the railroad diagram. The grouping element is usually a column name, and I think the examples I'll show here are going to be that way. The idea here is that we're going to take and condense together all the rows in the result set that share the same value for those grouped expressions. So if we're fishing out, say, as the example I just pointed out, if we're fishing out the revenue per state for my company, the condensation that I'm talking about here would sort of group together all of the rows in the intermediate result set that had the same value for the state name. It sort of squishes those things together. The other thing we can do in a group by is we can make use of what are called aggregation functions. You remember back when we introduced the select clause, the most common thing to show up in a select clause itself is going to be names of columns, maybe with a prefixed table name if there's redundancy. We can also have expressions more generally in the select clause. In fact, we can use the select clause as a 4-function calculator if we want. We can say select 2 plus 4, and it'll give us back a result set with a single element that has the value 6. More commonly, though, or more usefully perhaps, we can include aggregation functions. So in the case of this example where I want to get sales by state, I want to aggregate the individual transactions that take place within each state by adding them together, by coming up with their total or their sum. I could also ask for their average or their min or their max, and other functions are also available depending on the database that you're using. So here's an example of that, taken again from our DVD rental database. So we're doing a 2-table join. We've got payment and staff. And we saw before that the staff is basically the name of some human being that works at a DVD store, and the payment has to do with the amount of money that was paid for a particular DVD rental. And we saw in a previous example that we can join together the payment table, or we saw before that the payment table has a staff ID, and so I can use this on condition in the join to group together the payment with the staff person that is responsible for that particular rental. And then in the staff table that I'm joining here, I can fish out the first name and the last name of that staff member. So that's 2 of the things that I want to get in as a result of this query are the first name and the last name. But here's the new thing. I've got this aggregate function called sum, and it takes as an argument the columns in the intermediate result set that I want to add together in this case. I could also say min to get the smallest value, max to get the largest one, average to get the average value, and so forth. But I don't want to just get a list. So if I just stopped there, what I would get as a result of that query would be the first name, the last name, and individual price or individual amount for all of the rentals that were done by every staff member. So if we've got Mike and John here showing up as our only 2 staff members apparently, we would see Mike Hillier $2, Mike Hillier $4, Mike Hillier $4, John Stevens $12, John Stevens $2, right? All the individual payments that were made on those individual rentals would show up explicitly. But if I'm the sales manager and I want to, award the salesperson of the year, I want to know who made the most money, or who rented the highest dollar value of DVDs. So I want to get the total of those values. Well, in order for that to work properly, I've got to tell the query, I want you to take, if you go back and think of the results that I just described where Mike and John appear a whole bunch of different times with individual rental fees, what I want to do is kind of take that data and squish it down in such a way that Mike Hillier just shows up once and John Stevens just appears once. So for those columns, I'm going to just eliminate all of the redundancies. Now, if I just tried to do that, I'd have a problematic time doing that because the value of the rental payments are going to be different, which means that I'd end up with like Mike Hillier and $2 and Mike Hillier and $4 maybe just once. But that's not what I want to get. I want to have information about the total, the sum of all of those rows with the corresponding values in the first name and the last name columns. So what I do is, in addition to having this sum amount, I have a group by that says I want to group everything in this result set by the staff ID. So this is the primary key for this staff table. So we're not putting that in the output. If we had added, for example, staff.staffID to our result set, we might see that Mike is staff member 2 and John is staff member 7 or something like that. We don't show that here because we're not interested in that number for this report. But grouping against that particular column is how we're sort of squishing down that intermediate result set. So for everybody that is showing, for every row in that intermediate result set that has a corresponding value for the staff ID, that's going to be reduced down to a single row. And in addition, because I'm using the sum aggregation function here in the select clause, the way that the rows that differ, in this case, the rows that contain the total amount of total amount payment, the total amount paid for each rental, I'm going to add those things together. So for all of those rows that had a staff ID of 2 that corresponded to Mike here, all of his individual payments are going to be summed to yield this final result of $30,000 and change. I've backed out all of my little annotations here because I want to say a few things about easy ways to get in trouble with group by clauses. What we're seeing here when we group by that staff ID, let me just sort of write back in that same value from before. If Mike's staff ID is 2 and John's was 7, is that what I used? When we're doing a group by here, the database is going to assume that the fields that are mentioned in the select clause, first name and last name, are going to be unique with reference to the thing that you're grouping by. So the fact that I'm trying to group together by that staff ID, that'll work fine if, for that particular staff ID, Mike and Hillier, or the same values are present for the first name and the last name. And that's going to be the case here because staff ID is the primary key. And if I look at the first name and the last name from a row with a given primary key, that's guaranteed to be the same thing all throughout the table, right, by merit of the fact that we've got a primary key. Another way I could have written this that may be a little less confusing is instead of saying staff.staffID, I could have said group by first name, comma last name. All right? So I'm not using this primary key anymore. I'm basically just telling the database, go find the first name and the last name from all the staff and put them in an intermediate result set along with the amount of the rentals or amount of the payments that were made for rentals made by that staff member. Then, for those fields that are mentioned in the group by clause, squish all the rows together so that we end up with just a single row for the first name and last name that are mentioned in the group by. And then because we're not grouping by the amount, right? We got to have an aggregation function going on in the select clause to be able to combine together all of those amounts for the particular staff members. So the guideline here is whenever you're doing a group by, you want to make sure that in your select statement, you either are mentioning individual fields that have been combined by the group by, like we've got here for first name and last name, or fields from the intermediate result set that have an aggregate function applied to them. If you add any other fields to the select clause or remove those fields from the group by clause, the database will give you an error. Here's a more complex example of using group by. Let me show you the result set first here. What we've got in the DVD rental database is a film category, so things like sports and foreign films and family films and so forth. And the report that we're seeing here, this result set, shows the number of films in each of those categories. So that's what we're after. So go back to the query itself. We see that we are doing a query from the category table. That's the list of foreign, family, documentary, and so forth. We're joining that with a film category table. That's an associative table, right? Because we've got films that can have multiple categories and categories that can have multiple films. So there's a many-to-many relationship between films and categories that goes through the film category table. So this is a pretty straightforward inner join from clause that connects categories to film categories and ultimately to films, so that we can fish out the name of the film, the name of the category. And we're going to do a group by. So once we've gotten that intermediate result set that groups together categories and films with the corresponding entries in the film category table, we're going to group by name. And you can see here, to the point I made just a second ago about what can appear in the select clause when you've got a group by in force, is it can be either something that's uniquely determined by the group by clause, in this case it's the name column itself from the category table, or it has to be an aggregation function. In this case, we're using another function called count, which basically just counts the number of rows that are being squished together. So we're squishing together by name, and we're going to count the number of rows that get squished in the count aggregate function. The count needs to have some sort of an argument, and it doesn't really make any difference here what argument we give it. We're just giving it something convenient that corresponds to the title of the film, but there's no information obviously in this result set that talks about the film title, so it doesn't really matter what we put in there. Notice also that we're using an as clause. If we had left this out, the result set would have name over here, and then it would have count title over here, which is sort of clunky, doesn't look so great, makes it more complex to select that information from inside of a programming language that's using the database. So we give it a simple to use and simple to read alias for that expression. Again, this select clause is a list of expressions, which can be column names, but if there's something more complex than that, we'll often use the as clause to to rewrite that into something more convenient. So at the end, we have the list of all categories, and then we've squished down the intermediate result set such that every sports film gets squished down to one row, and the aggregate function counts up the number of those rows that got squished. Having is also associated with the group by clause. So if you think about the where clause as restricting the rows that come out of a select, the having statement does a similar kind of a job for the group by. So if we're doing a group by and we want to restrict the number of rows that appear in the result set after that group by, we use the having clause. And it takes, just like the where clause does, it takes a Boolean expression as its argument. And as I said, it's sort of similar to the rows, to the where clause, but for grouping together with the group by clause. So you use where with select, you use having with group by. So here's an example. I'm basically just taking that same query that we just looked at, right, getting the name of a category and the count of the titles in that category. The join clause is exactly the same. The group by is exactly the same, but I've added this having clause. So what I want to do here is, back to this result set, I've got various numbers of films in each of these genres. What I want to do is cut them off at a certain limit. I want to have all of the things that are more than a certain number. So in the having clause, I've got a Boolean expression. It's a comparison against a constant of 65, and I'm comparing the count of the titles in the intermediate result set. And the only values that will survive, or the only rows that will survive from the group by, are going to be those that satisfy this criterion. And you can see that I don't have any counts that are 65 or less in the result set. So again, just like the where clause constrains the select, the having clause constrains the group by. Finally, we can sort our results. By default, there is no sort criterion applied to the result set. It sort of comes out of the database in whatever order it decides to come out in. It might accidentally be sorted because of the way the algorithms are implemented internally, but if you want to guarantee a particular order, you need to add an order by clause. So the order by takes an expression, often again a column name, but doesn't have to be, as we saw previously. And we can ask for sorting in either ascending order or descending order, and we can actually have multiple sort criteria in play. So we can say order by first name ascending, and then go back around, comma, last name descending, and then exit to the end of the statement. So we can order by ASC or DESC. If we leave that off, as suggested by this sort of skip around arrow, the default is to sort in ascending order. So here's a simple example with an order by. We're going all the way back to our city and country examples. We're doing a join of city with the country such that the city's country ID matches the country ID of the country. And then we're going to do an order by. So we're going to order by country in descending order. And then within that sort order, we're going to sort by country in ascending order. And here's the result set. So we can see here that we've got countries that are sorted in reverse alphabetical order because we've got country descending. And within each country, we've got the cities. So here's a bunch of cities that are in Yemen. And you can see that those are sorted in ascending alphabetical order. And then here in Vietnam, we've got a couple of additional cities, and those are also sorted in ascending alphabetical order, even though the countries themselves overall are sorted in descending alphabetical order. So you can mix and match the columns and the sort orders to meet your requirements.